So some tooling considerations, again, the tooling enables all of these micro-molded components, and the machining is obviously extremely critical. Some of the things to consider, again, we don't have the industry standard for a tensile bar, for example, is about an 8-inch tensile bar. That really doesn't help us in the micro world, so we had to actually create a kind of a quasi-ASTM standard, but a very small tensile bar, 100 thousandths by 200 thousandths in length and width. And that is because we have parts in molds that have 2,000 gates or 3,005, 9,000 gates. That's a very small gate, so you're kind of shearing the material going through that very small gate. And most conventional sized tools are 20 or 30,000 gates. So you are shearing that material much more so than it's used to. And therefore we have to determine what we did with that extra heat, that extra shear, when it went through that injection mold. So we have to make these very small tensile bars to be able to test that polymer or test that metal, in the case of a metal injection molding, to see what happens to the part when it gets subjected to those very high shear forces. So we have really conventional sized or conventional tool making practices, CNC machining, EDM, wire EDM. They're just using extremely small wires, for example. In wire EDM, the smallest wire that's available is now about 7/10 of an inch, so a little bit less than 1/1000th of an inch. And EDM, we would certainly make the electrodes for extremely small machined components to be used in the mold. Injection mold down on the lower right-hand side, just to give you an idea, that's 3 by 5 by 5.5 inch minimum mold height. So you literally could hold this injection mold in your hand and dog it into the machine. It's kind of not conventional. Most injection molds require an overhead crane to actually place them into the mold, so this is a little bit different. So acceptable size tolerances or acceptable tolerances in conventional molds are not acceptable in micro molds, and I'll give you an example of that. When you have a 1/1000th or 1.5 thousandths wall thickness and your tool, your parting line coming together, for example, is 2/10 in Y and 3/10 in X, which you'd be very happy with conventionally if that's what you received, 2/10 and 3/10. But that 3/10 in relation to the 1/1000th wall, that's 33% of the wall thickness. So what's going to happen is you're going to inject the material down the fat side. It'll fill that side very easily, but the thin side it won't actually fill. You really have to be balanced fill to be able to fill some of these extremely small parts. So what we had to do in that particular case was we literally had to split that 2/10, 3/10 offset in tooling and create that 1/10 error to be able to fill that part. Not really conventional, but certainly required when you have parts this small. Some of the tooling methods we use, laser machining, EDM, wire EDM, which I just spoke about, ultrasonic machining, ion machining, CNC machining is the most common, chemical machining, photochemical machining, electrochemical machining. These are what we would call top-down methods, so you're actually removing steel or to create the part, or removing steel to create the tool that will then create the part. The bottom-up methods, the first several on the list, I won't profess to know too much about that, but it is actually growing features and growing parts that way. The only one we have used is LIGA, the one at the very bottom there, is a photolithography of really growing a layer upon layer of a nickel or a nickel alloy to create either a part or, again, a tooling insert would then create the part. So those are the current methods. I'm sure as we kind of get down the line, we will have to use some of these kind of growing from the ground up molecular type methods in the future.